Hi, everyone. My name is Anka Dragan. I'm a professor at UC Berkeley, and I work in algorithms for human-robot interaction, which is this cool intersection of machine learning and robotics and a little bit of cognitive science. So today I figured I would share a little bit with you about some of the thing that's, I think, most exciting to me about the type of research that we do, which is when we get robots to come up with interaction strategies, strategies for interacting with real people, sort of on their own without us having to handcraft that behavior. Just kind of emerge out of planning and learning. So here's how I got into that. I was doing my PhD back at Carnegie Mellon, and back in 2009, Google started their self-driving car project, and some faculty and friends went to California to join. And I believe it was around 2010 when I saw this article in the New York Times, I think, where it was reporting that apparently the car got stuck at a four-way stop, because what would happen is that the car would be there, would stop, a person was there, they would be inching forward into the intersection, and then the car predicted that they would go, let them go. And by the time they went, there was another human inching forward into the intersection. So this, would go on for a while. And so Sebastian Turin then commented how they had to program in this inching forward strategy for the car to basically make sure that it's asserting itself. So that's kind of a strategy that they had to program in that was useful for interaction. Now, at about the same time, my lab in grad school was doing this demo for research at Intel Day. And the robot would pick up these bottles and would hand them over to people in the audience. And unfortunately, this was really hard because people had no idea what the robot wanted them to do. So it would, here's the robot, here's the bottle, here's person in the audience. The robot would turn around, it would say, please take the drink. The person would not do anything. And then we had to kind of go in and explain to the person what the robot wanted them to do. Now, luckily, my friend Maya Chakma, who's now at UW, she visited the lab and she programmed in this super cool strategy called spatiotemporal contrast, where you'd hold the bottle in one way and then give it in a different way to sort of offer clarity about what that you're trying to give it to the person. And so that worked really great. So that's another sort of strategy that someone designed and programmed in that ended up being really effective. And then 1 year later, I attend HRI in 2011, and I get blown away by this paper from Leila Takayama. She worked with a Pixar animator to animate the PR2 robot and make it more intent expressive. So the animator designed these motions, and it was based on strategies like forethought and anticipation. And I saw this and I thought it was amazing. And I wanted it just so badly for robots to be able to generate this sort of stuff on their own. Kind of turn into Pixar characters. I thought that would be really cool. So here are all these examples of creative people designing these strategies for interaction, right? So based on forethought and stuff like that. And there's a spectrum, right? So some would just be at the concept level. Some would be instantiated by kind of designing, programming a specific motion. Some of them would be like this. This was the Leila paper. Some of them would actually parameterize the strategy, so write this bit of code that would sort of program the robot to generate the right motion and adjust it depending a little bit on the situation. So those were examples like Michael Gilniak had this work on programming anticipation and getting a recorded motion to exhibit more anticipation. So this was happening in HRI. In robotics, sort of similar approach. Sometimes this approach of designing a strategy and then parameterizing it so that the robot can sort of fill in the details. It was also popular there. So for instance, some people in the lab were doing touch-based localization. That was a thing. And so here you'd localize an object by doing a sequence of move until touch primitives. And so they would come up with this idea of moving kind of in a straight line until you sense a force. And then they thought this would be a good way to localize an object. And then the robot would essentially search for directions to instantiate this with that ends up localizing a particular new object with some particular initial uncertainty. And then I saw this thing by Rob Platt, where this was 2010. They gave this example of the light-dark domain. So here you'd have a start and a goal, and you have some initial uncertainty over where you are. And then you'd get observations from the environment, but these observations were more precise and less noisy when you're in the light than when you're in the dark. And Rob showed that if you approximated the solution to the POMDP that this induces, the robot would come up with this nice strategy of not just heading to the goal and hoping it gets there, but actually sort of being able to kind of deviate into the light until it gets confident enough and then shoot for the goal. And I really like this example because essentially, we don't have to tell the robot, oh, look, here's a strategy, here's move until touch, this is what you do. But instead, we formulated the problem the robot needs to solve, in this case, the POMDP, and finding a good enough approximation to that in general purpose approximation, it leads to the robot essentially inventing, if you'll allow me to anthropomorphize a bit, invent this strategy. So moving towards the light emerged from optimal decision making done directly over the robot's raw action space, rather than us having to first devise some primitives that encode a strategy and then do decision making over the parameters of these primitives. No, we just gave the robot the problem and it sort of figured out a strategy. And I think this is cool, and it's also practical because if you can do it, then you end up with this kind of strategy that adapts naturally to different situations. Like if you start in a different place, your sensors were slightly different and so on, that strategy sort of changes depending on your situation. So you get generalization. And so for HRI2, I started wondering, well, could we push the spectrum a little bit forward and have robots autonomously generate the strategies for interaction as well, instead of relying on us to design them? And I realized there was, there's pretty profound difference between doing this in interaction with people and doing this in robotics. Because in robotics, we usually we know the problem we're trying to solve, it's some POMDP, some robust control problem, whatever it is, we know it. And we know that if only we could solve it exactly, we would see the right strategies emerge in the solution. So emerge from first principles. So that means whenever we have to handcraft strategies, we at least understand them as approximating the optimal solution to the underlying problem. And in contrast, in HRI, we don't know the problem. So we don't know how to write the problem such that if only we computed the optimal solution would give rise to these types of strategies. So when we handcraft strategies, we're a bit kind of flying in the blind because we don't know how to generalize them, and we don't know if they're the right strategies, what they're approximately optimal with respect to, nothing like that. So we don't kind of get to understand them from first principles and analyze them. And so I got really excited about, well, can we formulate the problem for HRI so that these things, at least in theory, can emerge out of first principles? And this came out of scientific curiosity at first because I wanted to understand what these strategies are optimal with respect to. And it also came out of practicality because even if we can't perfectly solve these problems, we can come up with general purpose approximations that end up sort of scaling better and generalizing better. So that was the thought. Okay, so how does it work in robotics? How do robots come up with these strategies? Well, the way it works is pretty simple. You define a state space, you define an action space for the robot. You assume that there's some underlying dynamics model. You might know, or you might have to learn this. And some observation or sensor model that relates the evidence you get, the observations, with the underlying state. And then you have some objective function, cost, reward, loss, even constraints, and you do optimal decision making in this problem. And so now it seemed like we kind of need to take this in interaction and kind of add the human somehow, right? So now the state space is more complex. At the very least, it contains not just the physical state, but sort of the human state as well, internal and physical. And the thought was, kind of the guiding principle was that if I could just model enough about the dynamics of human state, I won't have to tell the robot how to interact. It can perhaps figure out how to interact on its own. The strategies can emerge out of decision-making in the system if we manage to capture enough about the human state and how that changes on its own in response to the robot. And I want to share with you that I've been surprised by how much we got with how little we modeled. Modeling people is really hard. But it turns out we didn't have to do that sophisticated modeling, and we got pretty far, at least so far. So we've seen this play out in different types of interaction, navigating around each other, collaborating on tasks, physically interacting, shared autonomy, handovers. And we've seen robots doing decision-making this way, kind of managing to invent strategies like inching forward into intersection, nudging, backing off, exaggerating their motion, probing at a person's intent and comfort preferences, kind of nudging people to better choices. All these strategies, some of which I don't even have good names for, honestly, were things that have resulted from decision-making in sort of the robot's direct action space when we modeled enough about the person. Okay, so how do you model things about the person? What does that even mean? Well, in the simplest sense, what we want to know is what the next human state will be conditioned on the current one. And this really boils down to asking, how will the human act from this state? Because where they'll be next depends on the action that they take, and with the action they take, that's a decision that they'll be making. The rest is just physics. So how do people act? Well, also back in 2009, 2010, Brian Seberg was also at SAMU, and he was working on modeling human actions for this pedestrian prediction task. And he suggested, sort of building on some previous work, that we could model humans as taking trajectories, sequences of actions, bolded here, UH, that are approximately optimal with respect to their own sort of human objective, their internal goals. And I often refer to this as the intent-driven modeling, and that in itself is not quite sufficient to get us nice interaction strategies, because it sort of leads to these stuck robots, like in the New York Times. Take, for instance, this kind of autonomous car in orange driving here next to a human in the white car. It needs to change lanes into the left lane. So if you do intent-driven modeling for the person, you'll easily predict what they want to do. They want to keep going forward. And then your car will be stuck letting them through and merging behind them if there's someone, if there's space, if not, if there's someone coming, kind of being stuck. So that's how it kind of gets us these really stuck robots that defer to the human all the time. And there's one missing piece here that fixes this, which is that this dynamics model is really a true dynamics model. It doesn't just depend on XH. You have to account for the fact that what's optimal for the human depends on what the robot does too. So the robot action get in there and influence the human's next state as well. So people don't act in isolation. They take the robot into account. They make predictions about what the robot will do and respond to that. And so in Dorsa's work, we made the human prediction a function of the robot's trajectory. And now we end up with this sort of nested optimization problem here, where we're trying to find out what the robot should be doing, but what the robot should be doing depends on what the human does, which depends on what the robot does. And so when you optimize with that, the result is now you get the car that can actually figure out that if it accelerates and goes in front of the human will slow down and accommodate. And this is what becomes optimal for the human to do, given this new robot behavior. So the robot can kind of reason through that. And I call this a strategy because I do it all the time in heavy traffic. I used to do it all the time in heavy traffic. I don't really drive that much anymore in the pandemic. But yeah, imagine that we somehow try to program this in. We could program this in, but we'd have to sort of tell the robot how much to accelerate, when to do it, how much to go towards the other lane. Those would all have to be parameters, and deciding robustly on those parameters would be, I think, really hard to do in a scalable way that accounts for all situations. Because we give the robot a model of the human and the influence it can have on the human, it can figure this out and it can generalize it. So you start far in front of the human, you don't have to accelerate as much. You start behind, you don't bother doing it, you just merge behind them, slowing down a little bit, because that's probably the best you can do. Then you plug in a different objective for the robot. So here the robot was actually trying to get the person to change lanes to the right lane. So it figures out how to position itself to have control over the person's lane change. And an all-time favorite, same algorithm, same model. At an intersection, the robot wants to get the person through the intersection as quickly as possible. And get this, instead of just waiting there, instead of letting the person go, it figures out that it can start inching backwards from the intersection, and that makes the person go through faster. And this actually worked in studies. So basically this backing off strategy, something that we know about in interaction, but here it emerges from planning with that dynamics model of the human. It's a very simple dynamics model, it makes a ton of assumptions, simplifying assumptions, but you're planning with that directly in the robot's control space, and lo and behold, the robot comes up with this backing off stuff. It's not some sort of primitive that we coded up, in fact, when Dorsa first saw this, she came to my office and was like, I got the results for our SS paper, but in this intersection environment, I think there's a bug because the card does some really wacky thing. And then she told me about it. I was like, no, this actually makes a lot of sense. And then it actually worked out with people. So that was cool. And then with Aaron Bestick, we also use the same model in robot to human handovers, a totally different situation. So in handovers, the question is, how do you give the object to the person so that when they take it, they can take it comfortably? And what we wanted to make sure is that the user can keep being comfortable when they use the object for whatever their goal is after the handover, after they take it from the robot. And so given the robot's choice of a kind of a grasp or handover pose, the human has these multiple options, like they can grab it this way or that way or that way. Forgive my kind of dummy human here. And so if the robot chooses now a different way to give it to the person has different options, different choices. So the human's choices are determined by the robot. And one thing that we realized was that people make these choices, right? This was our model from before. They make these choices depending on what the robot chooses to do, but in a typical scenario, what might happen is that the choices are actually a bit myopic. So you grab the object in the most comfortable way locally, but then you have to kind of bend and twist your arm to actually position it at the goal or re-grasp it or something like that. So, these are all the possible grasps that you have available, and you choose one that has very low cost for you when you grab it, but then has overall high cost when you actually move it away. And you omit, this other option here that would have been much better for you. So people are myopic. They think kind of one step ahead or a few steps ahead, not many steps ahead. And so we made this model be myopic. And then we made the robot have the same objective as the person, but actually plan for the full horizon. So now what the robot comes up with is this kind of grasping configuration for the object that is uncomfortable for the robot, but we don't care about that. But it leads to essentially whatever the most comfortable way for the person to get it ends up being comfortable when they use it as well. So this is the one that's being picked, and it's good myopically and it's good for the goal. So in other words, the whatever the tempting configuration is, the robot makes sure that's also good for the goal, and it eliminates these options for you that are tempting but they're actually really bad. And the closest analogy I have to that in the real world is kind of the strategy of nudging the user towards better choices is something that good designers do. For instance, if you look at bottles, I hear that they have this narrow neck. And that's there to incentivize you to grab it from there, because if you grab it from there, you don't warm up your drink as much. And you might not think about that, but the way the object is designed, it just naturally incentivizes you to do that. So it's kind of similar here. Nudging to better choices emerges from optimal decision-making directly over the robot's kind of control and action space once we account for human suboptimality in the dynamics. Okay, so far we've talked about being kind of having this fully observable, albeit under-actuated system where what you do influences what the human does. And I cavalierly had this model of the person where I wrote here capital UH, that's what the person wants. But the problem with what the person wants is that the person knows what they want. The robot doesn't necessarily know what the person's want. So we can think of this as there's this hidden variable here, theta H, that is in the person's head. Now the actions that people take, those are observations as well about what the person wants. And we can use that to estimate theta H and do optimal decision-making, sort of using in this partially observed system. So my next example of emergent behavior sort of speaks to that. So here this robot will move, and I won't like that it's keeping that cup too high up. So I push it down. And this is physical human-robot interaction. And there's many strategies proposed for how a robot should respond to physical human interaction. It can render an impedance. It can move in the direction of the human force. It can reject the human force. It can just go into gravity compensation mode. There's all these different strategies, and it's not clear which one is the right one. But if you look at this model of where human actions are evidence about human objectives, and if you're collaborating with the person and tell the robot to optimize for whatever the person wants, then all of a sudden the robot will naturally use these observations to update its belief about theta H so that it can do a better job at its objective. So in the work that I did with Andrew Bakshi and Dylan Lucid, so here the robot will interpret my push as evidence about what I want, and its reaction is to then plan to stay closer to the table. And again, this generalizes if instead I intervene and I turn the robot's end effector, it responds by continuing its trajectory but keeping the mug upright. And its response is not one size fits all, right? It adapts to the correction it receives and the context that it's in. So again, we see that generalization. Okay, now for cars, the same thing is needed. So here, the parameters theta H are kind of correspond to the person's driving style. And sometimes I've been shocked by this video over and over again every time I see it. This very aggressive truck driver that, I don't know if you saw it, let me kind of go back. So this person tries to merge in and the driver just keeps going. They're not letting them in at all. So in other words, they don't slow down. And if the robot plans on that, then that's not safe. So now if the robot understands that people might have these different driving styles, these different sort of objectives, priorities between safety and efficiency, and now if we get the robot to estimate the person's driving style and plan expectation over it, we're sort of back to those cars that get stuck. Because the issue is that they drive right next to you and they never get enough evidence that you would in fact slow down because you're just driving straight. So they never attempt the merge in the first place. And so we solve, the way we solve this problem is by getting closer to solving the kind of the underlying POM-DP. So there's an underlying POM-DP here where theta H is this partially is this hidden state. And if we solve the underlying POM-DP, the problem would get away because we'd get information gathering actions that gather more information about the person, make the robot realize that the driver is aggressive or defensive and act appropriately. An approximation that we've used is to simplify this and just incentivize information gathering in the robot's objective directly, which is a little bit like cheating. We're saying, take actions that sort of make your entropy of your next belief lower as well, just because we think that's helpful. So here now the robot nudges towards your lane, and I interpret the strategy that it comes up with as kind of a probing strategy. It's kind of the equivalent of going to the light in the light-dark domain. Because if you slow down, it gets information, it updates its belief and goes for it. But if you keep going like the truck driver, then it updates its belief and returns back to its lane. And then again, I wanted to emphasize the generalization. So same exact algorithm model now, four-way stop. The robot inches forward into the intersection, again, sort of seeking the light. And if you brake, it goes. If you don't, then it makes space for you to go. So inching forward emerged here from first principles. It was in no shape or form programmed in, and I think that's really important to restate. With Handovers 2, similar thing. The way the robot hands you over an object induces this sort of set of feasible ways for you to grab it, like we talked about. And your choice of how to grab it is now evidence about your ergonomic preferences, like what is comfortable for you. So we don't have to assume we know what's comfortable for people. We can learn it. And the way the robot hands you over the object can become this information gathering opportunity for you to kind of grab it in a way that's informative to the robot. So the handover itself becomes a query, a physically embodied query, I like to say, about what the person's preferences are. And then finally, with shared autonomy, if you're operating the robot towards one of these two goals, so you have goal A and goal B, the robot starts somewhere, use a joystick to operate it. The robot tries to figure out where you want to go so that it can help you. And so here's projecting everything in 2D. If I just infer passively, then what your goal is, right? You're operating towards the goal, and I'm planning an expectation over these two goals, and eventually end up figuring out that you want this goal and go towards it. When I optimize with info gain as well, just like we did in driving, it actually comes up with a strategy that kind of takes the person kind of quickly to the middle. And in the middle, you are much better at your input is better at disambiguating which goal you want. So by pulling it towards the center, towards the middle, it gains information. And that's completely a natural emergent strategy that when the robot is doing this optimal decision making directly in its control space. Okay, so this has really produced this wide range of strategies for us. And it's always, it's cool that the same approximation and the same sort of underlying dynamics model ends up kind of with adapting the strategy or even producing different strategies for different contexts, different situations, adapting automatically to the context. So as long as we capture enough about human state, I think it's really remarkable how much falls out of first principles. And that right there is really kind of this aspect of the research that we've been doing that I find the most exciting. So thanks for allowing me to share it with you today. And good luck, everybody, and stay safe wherever you are.
All right, so we're back and we have Anka Dragan with us today.
Hi, everybody. Good to be here. Thanks for watching the talk.
Yeah, we're really excited to have you here. So how the Q&A session will work is you all can paste your questions either into the Q&A in the Zoom or also in the Rocket chat. And yeah, let's get started. It seems like we have a question in the Rocket chat already. So, all right, here it goes. Can we model the dynamics of the agents and environment with similar algorithmic approaches? Just like human internal dynamics, we don't know the dynamics model of the stochastic environments.
Yeah, that question is really where this approach to essentially algorithmic human-robot interaction kind of started, the notion, or at least the type of approach that I've been talking about in the talk. It was really the realization that we can handle interaction with sort of the physical world, the environment already autonomously. Could we somehow port that over to the way we handle interaction with people? And that much like the way we think about interaction with the environment as we need to make predictions about how the environment will behave, right? How the environment will respond and what will happen over time. And I see the question Vidi is asking specifically about stochastic environments, right? Which are notoriously difficult to anticipate. That we maybe can think of people that way as well. And that's kind of where things got started, right? Let's talk about the dynamics of human state, physical and internal, and how the robot's actions are influencing all of that. Now we have to be careful though, because the two are not one and the same. So the umbrella approach, the umbrella formulation might start in the same way, but then the reason people are kind of different from the environment is driven by physics, right? People are driven by essentially the way they change is based on their decisions, based on the inferences that they have. So you kind of have to take that perspective and wonder, why aren't they arbitrary? Why aren't they acting in an arbitrary way? What's driving these decisions that are making? What can I have to say? And that's kind of leading to these more game theoretical approaches that I've been talking about, where you think of them as, oh, but they have an intent. I can present that as an objective. They're interested in optimizing for that intent, but wait, they're aware of the robot and so on. So the fact that they're agents in the environment, as opposed to just driven by the laws of physics, makes people particularly interesting aspects of the environment. And it often turns the problem from a single agent problem, the agent with its environment, to a multi-agent problem of the agent acting in the presence of another agent with unknown objectives, so under a partial information.
Yeah, thank you for that really good answer. Along that note, so for the information gathering strategies that you mentioned in your talk, especially when we're considering situations where we have multiple agents at play, do you ever experience issues or failure modes where the robot sort of gains misleading or ambiguous information that hinders it from achieving its original goal?
So the reason we started doing information gathering in the first place was because just observing people without intervening was leaving things too ambiguous. And so we said, oh, we have to do information gathering. We have to actually leverage the robot's actions to gain more information, to disambiguate what's going on. Now, that fails in kind of two ways. One way it actually fails is that no matter what you do, things are still ambiguous. So you have to kind of deal with that. But the other maybe more interesting way in which it fails is when you go and gather information, even though you don't need to. So the challenge with the approach we've taken so far is that it doesn't really reason about something called the value of information, right? So I should only gather information if it's really gonna alter my decision in some meaningful way, if it's really gonna impact the bottom line, if it's gonna impact the reward that I end up getting. But that's kind of a POMDP framework, and it's hard to solve these in continuous state and action spaces, particularly continuous action spaces. And so we kind of settled for this kind of proxy to that, where we said, oh, we're just going to incentivize information gathering as part of the objective. But unfortunately, what that does is the robot always has this incentive, regardless of whether it's actually useful or not. And there's tricks you can play, like you can say, I'm going to incentivize more information gathering if the belief has higher entropy, right? So there's more opportunity. So I actually need to learn something. There is something to be learned, but that doesn't mean that it's going to influence your decisions. And so we've been looking recently at ways to think about how we might be able to approximate this influence on the decision making, this influence on the reward, without actually going through the full POMDP solver.
Yeah, thank you for the really thoughtful answer. One thing I was curious about, so I think during your talk, you mentioned that there are all these emerging areas at the intersection of these disciplines, such as like human cognition and robotics and game theoretic approaches as well. In your opinion, are there any particularly specific emerging areas that you're excited about?
Yeah, I mean, these days, what I'm very selfishly interested in is something like CogSci meets behavioral economics meets machine learning for the purpose of modeling the biases, the suboptimality that people have. So where we're starting to get into trouble with the approaches that I was mentioning in the talk is that they're largely driven by these assumptions that people have some intent, but then the way that they act is approximately optimal with respect to that intent. In some places, we even use perfectly optimal, which is very much wrong. In some other places, we said noisily optimal, right? So some, very, very typical model we would use is kind of a Boltzmann, like Gibbs-like distribution. We say the probability of an action is proportional to the exponent to e to the kind of q value of that action, right? So the more rational an action is, the closer to optimal an action is, the more probable it is. But that doesn't mean that people take the optimal action. But now where that starts, that sort of papering over suboptimality with kind of just noise, right? It's sort of saying, well, people are acting differently, but I'm going to call that noise, and I'm going to say, well, there's this stochastic process then drawing from this distribution. It's a little bit better than like taking a Gaussian, and taking the optimal action, stuffing noise around it by a Gaussian. It's a little bit better than that. It's multimodal and so on, but still, it's really just kind of plastering over the actual problem, which is that people have systematic biases, right? They're not just saying, oh, I'm going to do something suboptimal. It's basically, there's all sorts of things, myopia, not thinking forward ahead is one example I had towards the end of the talk, but there's this thing called prospect theory about sort of we're risk averse, where there's just the confirmation bias. There's all sorts of things that people have found, and it's kind of like this list that's been building over decades of these findings of, look, we're biased in this way, look, we're biased in this way, look, there's this thing that we're doing, look, there's that thing that we're doing. So far, there's been relatively little sort of formalism behind it. There's a few theories, but we don't have this kind of comprehensive understanding of, well, what are these things that are at play? And that's really difficult from a robotics and AI more broadly perspective, right? Because you can't sort of sit down and encode every single bias and account for it. You need sort of some general purpose models that will learn from the individual and adapt, and that's it. And so thinking about how you can develop that, right? Thinking about how you can put everything under a cohesive umbrella that's kind of nicely parameterized by, not too many parameters, so you have a chance at adapting to an individual with within just a few samples, but not so, strict that it's rational or approximately rational, something more flexible. I think that's really exciting, and it's very much an interdisciplinary type of question. And I can talk more about that, but I just want to give you.
I see. So I think this was accidentally pasted in a private chat, but we have a question where, how do you think intelligence and the way we think about intelligence in human-robot interaction will change in the future? And I think this is particularly relevant given how you mentioned that we're not doing a great job modeling the suboptimality of humans. I think there's a lot of discourse on how we can always be optimal or rational.
Yeah, no, that's a really good point. That, and I'm not sure this is fully answering that question. I mean, maybe there's multiple answers I could give, but definitely one of them is being more mindful of realistic human behavior. And one of the things I've been excited about is to really cast human suboptimality less about being a problem with the human and more like being a problem with the robot not understanding something. So I like to say that people aren't really, they're irrational from a kind of a ground. If you know the ground truth, then they're not taking the right actions, but they might actually be much closer to optimal under their own belief about the world, the state of the world, how the world works, and so on. And so we've been kind of pursuing a bit of this kind of mini research agenda in the lab lately that's been looking at, well, if people are taking actions that seem really noisy or really weird, maybe the explanation is that they're observing the world in a different way than the robot is. And so their state estimator maybe that has some flaws or something like that. And so that's leading them to not know exactly what the state of the world is. And so they're taking a pretty reasonable action, but under the wrong assumption about the state of the world. Or similarly to that, maybe they don't understand exactly how maybe they don't understand the dynamics of the system, right? The transition function in an MDP. Like maybe they're acting in this world, but they're taking actions based on kind of an example is we have this notion of an intuitive physics in our head, right? That we have a simulator of physics, but it's not, at least we can't predict exactly what will happen with a dynamical system. We have some intuitions, but they're not perfect. And this appears very much when you put people in control of robots, especially complicated robots. If you have people pilot drones, or if you have people operate 7 degrees of freedom arms, right? That's really difficult for people. And it's difficult for many reasons, but we found maybe one of the reasons is that they're not familiar with the dynamics of that system. And so they're taking actions that are very suboptimal under the physical system, but perhaps they're actually close to optimal under their very simplified version of how the system works. And so if you account for that, then you can figure out what they're trying to do and then send the physical system where they're actually trying to do. So this was a paper in NeurIPS a couple of years ago. It's called, it had a cute title, like, "Where do you think you're going? Human beliefs, adjusting for internal dynamics," something like that. So this notion that, like, let's give people a bit more credit. Yes, underground truth, if they knew everything that the robot knows, they're suboptimal, but maybe their actions make sense. And I see that I have to shut up now because we're done. But thank you very much, Christy, for organizing this and for the wonderful questions. Thank you, everybody.
Yeah, thank you so much for all your answers. So that concludes the Q&A session. I think we had one remaining question. Maybe we can port that over to the Rocket Chat. But for now, WIML's president, Sarah Osentowski, will present the WIML closing remarks. So yeah, thank you, Anka, so much for joining us today.
Hi, Sarah. Hi, everybody. Bye. Take care.
Bye.